Welcome to this topic of the Demystifying IPv6 course on neighbor discovery. Neighbor discovery is just one of many topics of this Demystifying IPv6 course. So what is neighbor discovery? Well, neighbor discovery is defined by RFC 4861. It's a protocol that replaces IPv4's ARP, or Address Resolution Protocol, plus it adds many new features. It uses the ICMP version 6 messages, as described in the previous topic, as its basis for its protocol exchange. Neighbor discovery messages set the hop count to 255, which is the maximum allowable value for that field. In other words, all 8 bits set to 1. And this disallows remote hacking because if any packet came from a subnet other than the one that it's received on, then it's not considered a valid neighbor discovery packet. In other words, neighbor discovery should only be performed between two nodes that are on the same subnet. Neighbor discovery is used for a variety of features, such as to find the link layer addresses of neighbors. In other words, their MAC, media access control addresses, such as an Ethernet address. To find neighboring routers. In fact, there are special neighbor discovery messages that routers can use to announce their presence and certain information. It also is used to actively keep track of neighbor reachability. It sends network information from routers to hosts and is used for host auto configuration. It could also be used for duplicate address detection, or DAD. The usage of neighbor discovery is a set of messages and processes that determine relationship between neighboring nodes. Like I mentioned previously, it replaces IP version 4 ARP. It also replaces ICMP version 4 router discovery and ICMP version 4 redirect. Neighbor discovery is used by nodes, so in other words, for any type of node, whether it's a host or a router, for duplicate address detection, to determine link layer address changes, and to determine neighbor reachability. Neighbor discovery is used specifically by hosts to discover neighboring routers and use that information for auto configuration of its address to assign its prefix and other configuration parameters, as we'll see a little later on. Neighbor discovery is used by routers specifically to advertise their presence, to announce host configuration parameters, and on-link prefixes. It is also used to inform hosts of a better next hop address to forward packets for a specific destination. As I've mentioned many times already, neighbor discovery uses the ICMP version 6 control plane protocol to exchange its messages. So the top graphic depicts the IP header with the next header field set to 58, which is a value that indicates ICMP v6. And then you have the ICMP header, the common header, which is a type, code, and checksum followed by data. An ICMP type message 133 through 137 is used for neighbor discovery messages. So the different types of neighbor discovery messages, you have router solicitation, which is type 133. It's used by hosts to request routers to send an advertisement immediately, as opposed to waiting a minute or two for the next router advertisement to be sent automatically. The router advertisement type 134 is an advertisement I just mentioned, and in it contains one or more prefixes. It has a lifetime, and it's used for either stateless or stateful auto configuration. And we'll talk more about that a little later on. A neighbor solicitation message type 135 is used by a node to get the link layer address of a neighbor, whether that's another host on the same subnet is trying to communicate with, or a router if it's trying to communicate off subnet. A neighbor advertisement message is type 136. It's used in response to a neighbor solicitation message just mentioned. And finally, a redirect message type 137 is sent by routers to inform a host of a better next hop node. So this slide just gives a little bit more detail on the different types of messages, whether we're talking about router solicitation or router advertisement, neighbor solicitation, neighbor advertisement, or redirect messages. They're sent for different reasons that we'll cover in the following slides. So let's look at a neighbor discovery example and the four-step process. The next 4 slides will demonstrate each of the 4 steps separately. So for the 4 steps, assume number 1, that host A wants to communicate with host B. In order to do so, step number 2, host A needs to determine a valid multicast MAC address for host B. In other words, a MAC address that host B is listening to that pretty much only host B is listening to, and as opposed to sending it to broadcast as was the case with ARP and IP version 4. Step number 3, host A is then going to send a multicast neighbor solicitation on the wire, and theoretically only host B or a very limited number of hosts will be listening to that particular address. And then finally, step number 4, host B will send a unicast neighbor advertisement to host A. So step number 1, again, assume that host A wants to communicate with host B. The question is, how does host A know host B's unicast address? So in this graphic here, item number 1, which is a unicast IP address of host A, depicted in green here, is what host A knows. And how does host A know that? Because it determined that most likely using the DNS, domain name service. In fact, in this example, it's host B's link local address, but it could be any globally unique address that's assigned to host B. The problem is host A does not know host B's unicast MAC address. So host A knows host B's unicast IP address, but it doesn't know a MAC address of which to send messages to. Step number 2, host A needs to determine a valid multicast MAC address for host B. Well, how does it do that? So there are different steps that it goes through. It first converts host B's unicast address, depicted as item number 1, the unicast IP address, to its SNM, solicited no multicast address, which is depicted as item number 2. One thing you might notice on this slide is the least significant 24 bits of each different type of address, whether it's the IP or the MAC address, is depicted in red, and in fact they're all the same for the host B, which is 0260A5. So host A can determine from host B's unicast IP address what its SNM address is, starting with the prefix FF02:1:F, followed by the least significant 24 bits that I already mentioned. From that, we described earlier in a previous topic on the IP addressing part 2 how to map down a multicast IP address into a multicast MAC address. So the SNM address FF02:1FF/104 prefix ends in the least significant 24 bits of the host MAC address. I can then map down actually the least significant 32 bits of the SNM address. So in other words, starting with the FF and then FF0260A5 to a multicast MAC address that host B has registered its NIC with and is listening for. It would always start with the 3333 prefix as I described earlier. And so now host A knows a multicast MAC address that for the most part only host B is listening to. This is the key to eliminating broadcast in IPv6, is I can reverse engineer from your IP address a MAC address that you're actually using without actually knowing your burnt in hardware address. So step 3 now that I've determined all the information I need, I'm going to send a multicast neighbor solicitation onto the wire. Of course, that particular solicitation packet is going to propagate in all directions, so both host B and C will see it, as well as other hosts on the wire, but for the most part, only host B will be listening to that destination MAC address 3333 FF0260A5, which again was derived from host B's SNM address, which again was derived from host B's unicast IP address. And so only host B should read in that packet. Host C will probably ignore it, especially since it's not sent to broadcast. But then host B can double check inside the neighbor solicitation header for the target address, the FE80 address that I mentioned earlier, just to double check that it is indeed for host B. Once host B has determined that the neighbor solicitation packet is for it, it will send a unicast advertisement back to host A. So now that we both know each other's unicast MAC addresses, we don't have to deal with multicast either at the MAC layer or at the IP layer anymore. And so host B can return his burnt-in MAC address, and now they can both use each other's burnt-in MAC addresses to communicate. Well, these MAC addresses that I'm mentioning to are stored into a neighbor cache. The neighbor caches are fairly dynamic as opposed to the way it worked with ARP, where the ARP caches were fairly static and all they had was a 15-minute timer associated with them. So no matter what, I always assumed that you were present for at least 15 minutes, and when that timer expired, I would send a new ARP, even though you may still be in what would be considered a reachable state. So IPv6 has a state machine that it goes through to determine reachability. So obviously it starts off with no entry, and then it sends the multicast neighbor solicitation as I mentioned before, and until it actually gets a neighbor, the unicast neighbor advertisement that I mentioned before, it will be incomplete. But once it does, it's going to transition to a reachable state. Now, it will actually stay in just a reachable state for a short period of time in terms of seconds, and so it will almost immediately go to stale. Stale is not necessarily a bad state. It just means you're transitioning to the delay state where you're going to probe if necessary for reachability again, meaning that you could actually use feedback from your upper layer protocol such as TCP or UDP to confirm that reachability still exists. In other words, you're exchanging packets, and transition from the delay automatically back to reachable and again back to stale and then to delay. Or if there is no upper layer protocol exchanges going on, then you can send a probe message proactively. In other words, send another neighbor solicitation, and if you get a response, you can go back to reachable, but if not, you're going to go back to no entry exists. And so you'll transition through this state machine, continuously as long as you want to communicate. Duplicate address detection is used when a device first boots up and it obtains its IP information one way or another, which we'll discuss in another slide, and then to determine if that IP address that it's configured itself with is actually already in use by another host. So with DAD, you actually send a neighbor solicitation. It would actually be a multicast solicitation, but you base everything off of your own configured IP address. So in other words, you convert your configured unicast IP address to the S&M address, map that down to a multicast MAC address, send it out as I described earlier, and see if anybody else responds. In other words, somebody else is also listening to that destination multicast MAC address and looks at the target address in the neighbor solicitation header, and it is for them as well. And so they would respond, and you would determine that somebody else is already using the IP address that you've configured yourself. Router advertisements play a big part of the IPv6 protocol operation. So this slide depicts the router advertisement message. I'm not going to break out all the fields here, and some of them are broken out on the following slide, but two very important bits, the M bit for managed and the O bit for other configuration, are referred to as flags and are used for host auto configuration. So the idea is if the M bit is set, it says it's managed, which also is referred to as stateful address configuration, which means you should be using a DHCPv6 server instead of using the router advertisement directly to configure your IPv6 address. Otherwise, if the M bit is not set, it means you will use the router advertisement directly to get your prefix and possibly other information. The other flag basically says that even though you are using the router advertisement to configure your IP address, you're still going to use a DHCPv6 server for some other configure information, such as what are your DNS servers that you should use. So this slide depicts a multicast router advertisement, and so you can sort of parse through and look at things. For instance, the destination IP address is the FF02::1, which is all hosts on this link. And again, just like any multicast IP address, it maps down to an Ethernet MAC address beginning in 3333 with the least significant 32 bits equal to the least significant 32 bits of the multicast IP address, which again is just ::1, so it's all zeros ending in 1. So essentially all hosts on the wire will be listening to that destination MAC and that destination IP address, and they'll receive the router